and today Dominic Joyce will give his second lecture on orientations of modular coherent sheaves on Calabi-Yau fourfolds. Dominic, please.
Thank you. So this is based on a big paper which appeared on the archive recently. Everything I talk about is joint work with Markus Upmeier. I believe that Jan will post the I believe Jan will post the slides in the chat. So here are a few references. Yeah, so let me recap from the last lecture. So if X is a projective Calabi-Yau four-manifold over the complex numbers, and M is the derived moduli stack of coherent sheaves, or perfect complexes on X, then M has a -2 shifted symplectic structure in sense of PTVV. This gives you an equivalence from the tangent complex to the cotangent complex of M shifted by -2, and an isomorphism of determinant line bundles from the dual of essentially the canonical bundle of your moduli space into the canonical bundle itself. Then we define an orientation on our moduli space to be an isomorphism, kind of trivialization of the canonical bundle of M, such that this given isomorphism is of the form phi composed with phi star. So it's basically a square root of this isomorphism determined to omega. And we need orientations to define Donaldson-Thomas type invariants of Calabi-Yau four manifolds, counting coherent sheaves, semistable coherent sheaves on your Calabi-Yau fourfold. So that's a problem in algebraic geometry. I'm going to talk about means of proving orientations exist on such moduli spaces and constructing canonical orientations. And the story goes through differential geometry, quite a lot of algebraic topology. So a whole mix of different techniques. So let's suppose that P is the principal U of M bundle on our 8-manifold X, and BP is the topological moduli stack of all connections nabla on P, up to gauge equivalence. Then we can define a principal Z2 bundle, OP over BP, of what we call orientations on BP. So well, BP is really infinite dimensional. But these are orientations of the kind of Fredholm operator, the positive Dirac operator, twisted by the adjoint bundle of this principal UM bundle P, and using the connection to make this operator. So an orientation on a Fredholm operator is basically an orientation on the determinant of the top exterior power of the kernel tensored with the dual top exterior power of the co-kernel. And this turns out to be a natural thing to look at. So by some work by myself and others in 2018, if you can build orientations on these spaces BP, you can pull them back to orientations on, well, at least the substack of M, which has Chern character the same as the Chern character of P, and actually you can, with a bit more work, you can get an orientation on all of them. So if you can prove orientability or define canonical orientations on these spaces BP, then you can deduce orientability, or you can define canonical orientations on our algebraic geometry moduli spaces M. So today I'm going to not talk anymore about the algebraic geometry story. I'm going to talk about this problem of how do you find orientations on these moduli spaces of connections on your manifolds. So I defined what I call the bordism category. In this case, for UM bundles on 8 manifolds, it would be called board 8 spin of BUM. This is a Picard groupoid, a kind of two-category version of an abelian group. And we also define an orientation functor which is the symmetric monoidal functor from this bordism category to super Z2 torsors, which is also a Picard groupoid. And I told you that choices of orientation for the moduli spaces BP for all principal bundles P over X, where your choice should be invariant under isomorphisms of principal bundles. A set of such choices is equivalent to a trivialization of this functor on a subcategory of this Picard groupoid, depending upon the manifold X. Now, this Picard groupoid and this functor are explicitly computable, provided you're able to compute spin bordism groups like the spin bordism group of the classifying space of when n equals 8 and 9, using algebraic topology. And by doing such computations, we can answer questions about orientability and canonical orientations for moduli spaces of this kind. Okay, so today I'm going to tell you more about this story. So let me first talk about bordism, in case it's not something you're familiar with. So for me, B is something I call a stable tangential structure, or manifolds. It's basically a type of manifold. So we could be talking about unoriented manifolds, or oriented manifolds, or spin manifolds, where for me, a spin structure on a manifold includes an orientation. So there's a whole bunch of different stable tangential structures, for example, stable unitary and so on. Each such tangential structure determines a flavor of bordism. So for each topological space, which you might want to assume is nice, homotopy plus theoretical complex or something like that, and each integer n greater than 0, you define the bordism group, omega nb of t, to be the set of equivalence classes square brackets xf of pairs round brackets x and f. But here x is a compact n-dimensional manifold with B structure. So it could be a spin manifold, for example, and x has empty boundary. It's and f going from x into t is a continuous map. And the equivalence relation we use is that x0, f0 is equivalent to x1, f1. If there exists a compact n+1 dimensional manifold y, which has boundary x0 together with x1, and y should also have a B structure. And we want a continuous map, G, going from y into t, such that y has boundary minus x0 together with x1, and G restricted to the boundary of y as f0 together with f1, disjoint union. Here, minus x0 is x0 with the opposite B structure. So, for example, that would mean the opposite orientation. If you're working with oriented manifolds, there's also an opposite notion of a manifold with a spin structure. Okay, so then this bordism group, I've defined it as a set, but it's an abelian group. The addition is just come from disjoint union of your manifolds and disjoint union of the maps. The identity is the empty set. And negation in your abelian group takes x to minus x by this changing the sign of the B structure. Okay, so it turns out that bordism is a generalized homology theory. So it satisfies all of the Eilenberg-Steenrod axioms of homology, except for the dimension axiom, which tells you that, well, the dimension axiom says that the bordism groups at the point, well, the homology groups at the point are only non-zero in degree 0. Because it doesn't satisfy the dimension axiom, the bordism groups at the point can be non-zero for arbitrarily large n. Okay, so these generalized homology theories, they satisfy most of the usual package of properties of a homology. For example, you have lots of long exact sequences and that sort of thing. And there is an Atiyah-Hirzebruch spectral sequence going from the homology of your topological space T with coefficients in the bordism groups at the point, the Q bordism groups at the point. That spectral sequence converges to the bordism groups of your manifold T. So if you're cunning with spectral sequences, then you may be able to actually compute these bordism groups, and we do quite a lot of that. If T is path connected, then the reduced bordism, okay, so because it's a homology theory, there's also a relative homology theory version of it. Reduced bordism is, I'm going to twiddle, T is the relative bordism of T relative to some choice of base point, doesn't matter which. And then in this case, there is a natural splitting. So ordinary bordism of T is the direct sum, canonically, of the reduced bordism of T and the bordism groups of a point. So let's talk about spin bordism groups of classifying spaces. So, for example, if G is a Lie group, it has a classifying space BG, which is topological space, natural up to homotopy equivalence, such that principal G bundles and topological space are essentially the same thing as maps from a topological space into BG up to isotopy. So we're going to care about spin bordism groups BT when T is a classifying space such as BG, or possibly a loop space such as the loop space of BG. And you can compute these using algebraic topology. I should say that my collaborator, Markus Upmeier, is the one that did nearly all the work in computing all of these bordism groups for us. So it's known that the bordism groups, the spin bordism groups of the point are, they're given in this table, up to degree 9 at least. They're either they're made out of Z's and Z2s. And you can explain these, these are understood very, very explicitly. For example, this is generated by the circle with the non-trivial spin structure. The homology of classifying spaces, let's say over Z or over Z2, is also known for classical Lie groups G. You can just go and look them up in the literature. People care about, for example, the cohomology of BG because that determines characteristic classes for principal G bundles. And if you know the cohomology, then you can work out the homology by the universal coefficient theorem and so on. So using the Hirzebruch spectral sequence, okay, I've written down the version which is for reduced, it goes from reduced homology to reduced bordism. Using that Hirzebruch spectral sequence, we can prove, for example, that BSUM for M large enough, let's say M at least 5, has these reduced spin bordism groups. They're 0 in degrees 0, 1, 2, 3, and 5. You get Z in degree 4, Z in degree 6, Z cubed in degree 8, and Z2 in degree 9. So for the Calabi-Yau fourfold problem, we need to know these two bordism groups. We need to know them not just as abstract abelian groups, but we want to understand what they mean. So we give explicit basis elements for these groups. So the 8-dimensional group would be generated by 3 8-manifolds with 3 maps to BG, which or BSUM, which are equivalent to the choice of 3 SUM bundles on 3 manifolds. And we can also describe the isomorphisms explicitly. So, for example, the isomorphism from the 8th spin bordism group here to Z cubed can be written by saying, well, we write an element of this bordism group as an 8-manifold X, a compact spin 8-manifold X with a principal SUM bundle P. And then this map can be given in terms of integrals over X of various combinations of the Chern classes of P and the first Pontryagin class of manifold X.
Dominic, why do you need explicitly describe, say, generators or whatever? Why it's knowing the group is not enough? You want to prove that something is orientable for particular representable elements of your cube or whatever. So
Well,
why?
It helps to have explicit basis elements in order to compute the action of orientation functors. Because let's say I want to know how some orientation functor acts on this thing. I can compute. I'll want to compute an index on the manifold X. It will be enough to do it for the three basis elements of that thing, for example. Also, typically you have to work. We work with explicit basis elements in actually computing these groups, because there's a whole bunch of extension problems in going from the kind of infinity page of the Hitchin spectral sequence to the actual groups, and yeah, and it's just sometimes it's useful to have representatives for things, just to understand what's going on. Okay.
Just a second on the previous page. Yeah, why the 7 is missing?
Sorry, that should be there as well. The
7 is also 0, right?
That was just misprint.
Yeah.
Okay. So a Picard groupoid, or abelian 2 group, it's a groupoid G, so that's a category with all morphisms invertible, with a monoidal structure. So that's a way of kind of tensoring together both objects and morphisms in this category, which is symmetric and associative up to coherent isomorphisms. And you have an identity object such that all objects in G are invertible. So these are very algebraic objects. They're actually classified by 2 abelian groups, pi0 and pi1. Pi0 is the set of isomorphism classes of objects in G, with the addition in there is given by a tensor product of objects. The identity is the class of 1, and by assumption that gives you a monoid, but by assumption everything's invertible in there, so it's a group. Pi1 is the automorphism group of the identity object. It's actually forced to be abelian by the assumptions. And the third piece of data is a map Q from pi0 to pi1, which is both linear, meaning additive, and also quadratic. Okay, so, and symmetric monoidal functors between Picard groupoids and monoidal natural isomorphisms can all be classified by this group data of this kind. So for example, a symmetric monoidal functor would induce morphism from the pi0, the first thing, to pi0, the second one, and pi1 to the pi1 in a way which had to commute with the maps Q. Okay, so we define bordism categories. So they are geometrically defined Picard groupoids. As an example, if we take B to be a stable tangential structure, N some positive integer, and G a Lie group, we can define a Picard groupoid board N BG, B of BG to have objects pairs X and P of a compact n-manifold X with empty boundary and with B structure, and a principal G bundle P over X. And the morphisms are kind of relative bordism classes of a compact n+1 manifold Y with B structure with boundary minus X0, disjoint union X1, and a principal G bundle Q on Y, which restricts on the boundary of Y, which is X0 together with X1, to the P0 and P1. So that's a very geometric definition. It turns out that the classifying data, the abelian groups are pi I is omega n plus I B of BG, if I is 0 and 1. You can kind of see that directly because a principal G bundle P is equivalent up to some kind of homotopy to a maps from X into BG. And a map from X into BG defines a bordism class. So we chose this notation here to make it look like the bordism groups which classify it. So the BG here is just because it's classified by B bordism groups of BG. And the map Q going from pi I to pi I plus 1 has the effect of multiplying by the circle, where the circle is given the, well, potentially the non-bounding B structure if there is one. And then, okay, we can generally compute these groups and the map Q explicitly. So that means that although this is a very geometric object, we can understand it algebraically. Okay, so we define orientation functors, which are symmetric monoidal functors from a bordism category to either the Z2 torsors or super Z2 torsors. Orientations are typically a Z2 choice. If you have a moduli space, if it has an orientation, or if it's orientable, then there will be two orientations for it if it's connected, so that the orientations will form a Z2 torsor. So these orientation functors are defined using analysis of elliptic operators. In our paper, usually twisted elliptic operators, but there are other orientations problems where you could use different elliptic operators. And they encode orientation problems on moduli spaces. So, for example, the functors which control orientations of moduli spaces are spin 7 instantons in 8 dimensions, and in the case G is UM for M large, and also control orientations of moduli spaces coherent sheaves on Calabi-Yau fourfolds, are functors FG, going from Bordeaux spin of BG into the super Z2 torsors. They're defined by twisting the positive Dirac operator on the compact spin 8 manifold X by connections nabla on principal G bundles P. Okay, so functors of this kind are classified by group morphisms F0 from spin omega 8 BG into Z2, and F1 going from omega 9 BG into Z2, with F1 of Q is Q primed of F0, where the Q primed is actually the identity map on Z2. So these F0s and S1s are computable with some work. So for example, if I go back to my previous example of the bordism groups, if G is SUM from at least 5, F0 and F1 are 0 on the part of the bordism group which comes from the point. On the reduced bordism groups, F0 is a map from omega twiddle 8 BSUM, which is Z3 into Z2. This maps X, Y, Z maps to Y mod 2 in the particular basis, Z3 basis of this, which I chose. F1, well, both of these are Z2, and this is just the identity on Z2. So we can compute this map F0 by applying the TS Singer index theorem. We could do this by choosing a basis of three basis elements of this Z3, and then computing the indices of three elliptic operators on the 8 manifolds. In fact, there is no index theorem to compute F1, because F1 is really taking a kind of mod 2 index on a 9 manifold, which is a slightly strange thing to do. And there isn't an index theorem for that. However, in this case at least, you can determine F1 from this equation and the fact that the Q is essentially surjective. The Q going from the 8th bordism to the 9th bordism group is surjective on this part, the reduced bordism, and therefore we can know what F1 is by knowing what F0 is. Okay, so we can compute these bordism orientation functors algebraically rather explicitly. Let's now talk about factorizing orientation functors. This is a kind of general technique which I'll illustrate. Let's suppose rho going from G into H is a morphism of Lie groups. Then you can define a monoidal functor from the bordism category of G to the bordism category of H, which maps the pair of X and P, where P is the principal G bundle, to the same manifold X with the induced H bundle, where we define that principal H bundle by dividing out by G, where the G action on H comes from this morphism rho. Okay, so we call rho of complex type if the map it induces on Lie algebras from G into H is injective, and the quotient H over the image of G. This is a representation of G, and this quotient G representation should be the underlying real representation of a complex G representation. That is, there should be a complex structure on M, which is preserved by the action of the Lie group G on there. So if this happens, it turns out that orientations of moduli spaces of H bundles induce orientations of moduli spaces of G bundles, essentially. The reason is that somehow the difference between the orientation of a G bundle and the orientation of the corresponding H bundle is, well, the two elliptic operators differ by something which is complex, because it comes from this complex vector space H over G, and complex vector spaces are automatically oriented as real vector spaces. Okay, so then it turns out that in this case there is two commuting diagrams of, so the orientation functor for G factors via the orientation functor for H. So this tells you that if some n-dimensional moduli space problem is orientable for principal H bundles, then it's also orientable for principal G bundles, because you can essentially pull back the orientations along this functor. Another thing you can do is that if G is a product of H and T, where T is an abelian Lie group, then the G the moduli spaces of the principal G bundles are orientable if and only if the corresponding moduli spaces of principal H bundles are, because abelian groups give you kind of trivial orientation problems. And if this functor between bordism categories is an equivalence of categories, then you get both directions. The G problem is orientable if and only if the H problem is. You tend to get equivalence of the categories in the stable range when you have groups like SUM or U of M or whatever, which depend on integer. So the inclusion from SUM into SUM plus 1 for M large enough will give you an equivalence of categories because the bordism groups stabilize as M gets large enough. Okay, so these gives us a bunch of techniques for deducing orientability for moduli spaces of one principal group from orientability from a different principal, different Lie group.
Just a quick question. Earlier, you have an assumption for the SUM. M is at least 5.
Yeah.
And also for N, you ran from 1 up to 9. So that was because 2M at least satisfy that condition, right?
Yes. Well, so what I gave you was the stable answer. Essentially, I was giving you the bordism groups of SU, but in the range n up to 9, which I actually put on the slide, that would be true for 2M at least 10 for n is 9.
I see.
So that's where the M at least 5 came from.
Yeah, thank you.
Okay. So using these techniques, we can show that if you have orientability for the group E8, then you can deduce orientability for any G in this list by a combination of the complex type. Well, so basically, you can get all of these things out of for small m, you can get all of these things out of E8 by complex type morphisms with abelian factors, and then you can increase the m by using this equivalence of categories trick. Okay, so what we're going to do is we're going to settle the issue of orientability for E8, and then we're going to deduce it for all these other groups. In particular, UM is the orientability problem we care about in relation to coherent sheaves on the Calabi-Yau fourfolds. Okay. In fact, there are a whole bunch of different classes of bordism categories that we talk about in our paper. Not just the gauge theory ones. One is cohomology bordism categories. So if R is a commutative ring and K is between 0 and n, we can define the cohomology bordism category, if you write bord n B of K of R comma K, have objects X and gamma, where X is a compact n-manifold with B structure and empty boundary, and gamma is a K cochain in cohomology with D gamma as 0. Also, gamma is defining a cohomology class in the kth cohomology of X with coefficients in R. But it's slightly more than that. We want an actual choice of a cochain, a cocycle, rather than simply the cohomology class. Then the morphisms are kind of bordism and cohomology classes of a compact manifold Y whose boundary is minus x0 and x1, and a K cochain delta on Y whose boundary, or, well, that's not the right way to say it. So I should have said the restriction of delta to the boundary of Y is this. This is not really the boundary of delta. So then this bordism category has invariants the n plus ith bordism group of the Eilenberg-MacLane classifying space, K of Rk, for classes in kth group cohomology over R. So that's why we chose this notation, because the classifying the classifying groups are the bordism groups of these Eilenberg-MacLane spaces, and we can often compute the bordism groups of Eilenberg-MacLane spaces. Okay, so there is a highly connected, a 16 connected map from the classifying space of E8 into K of Z4. So basically, E8 has one characteristic class, a kind of second Chern class, basically, one interesting thing. And this characteristic class of E8 in its four-dimensional integral cohomology determines, therefore, a map from there to KZ4, and this induces isomorphisms on the homotopy groups up to dimension 16. So therefore, also the bordism groups of BE8 and of KZ4 agree, but n less than 16. And we can define a symmetric monoidal functor from the gauge theory E8 bordism category to the cohomology KZ4 bordism category, which is an equivalence of categories if n is up to 14, because we need the bordism groups integrating dimensions n and n plus 1 to be isomorphic, which we get here for n is up to 15. Okay, so in that way, we can translate orientability questions for E8 gauge theory into problems about this cohomology bordism category, which you can express in terms of cohomology and cohomology operations, such as Steenrod squares. So somehow the complicated E8 stuff goes out of the window, and we end up asking questions which we can answer using algebraic topology. Okay, so let's talk about how these things relate to orientations of BP. Let's take X be a compact spin n-manifold. I'm going to restrict to n is 1, 7, or 8 mod 8 because in the other degrees, the spin bundles are either complex or quaternionic, and therefore the Dirac operators are kind of, there's no orientation problem there because complex or quaternionic vector spaces are automatically oriented. So these are basically the interesting degrees or dimensions. in which Dirac operators have orientation problem. Okay, and like GBLE group, so then we define a subcategory, board X spin BG inside the this Picard groupoid, to have objects X and P where X is fixed, and have morphisms, but P can vary. The morphism have the manifold Y is fixed to be X cross 0, 1, and then Q can vary. So then we write inc for the inclusion of this subcategory as a functor. So for each principal G bundle P over X, it's a modulo stack BP, which is AP over GP, of connection is Nabron P modulo gauge. And there's a principal Z2 bundle OP of a BP of orientations for the twisted Dirac operators, either the Dirac operator or the positive Dirac operator, depending upon n. And I told you last time that the choice of orientation for BP for all P's, invariant under isomorphisms of principal G bundles, is equivalent to a choice of natural isomorphism in this diagram of functors. So we start with board X, with the special category for X. We include it in the bordism category G. Then we take the orientation functor for G into super Z2 torsors. We forget the Z2 grading to map to Z2 torsors. And then this up here is the constant functor with that which sends every object to Z2 and every morphism to the identity map on Z2. Okay. So we're expressing our orientation problems in a rather categorical way. Okay, so from this picture we can easily deduce that well, if n is 178 mod H, X is a compact spin n manifold and G is a Lie group, then BP is orientable for all principal G bundles P over X.
Sorry, Dominic, what means n comparable with 8 modulo 8? What's a strange notation? 8 modulo...
Or 0 mod 8 if you prefer.
Yeah, I mean, maybe there is a reason why you want to keep...
Oh, yeah, the reason is that I'm primarily interested in the cases n is 7 and 8.
Oh, okay. All right.
So, you know, we do G2 geometry with when n equals 7 and spin 7 and Calabi-Yau fourfold geometry when n is 8. So that's why we wrote it that way.
Okay.
Okay, so X is a compact spin n manifold, G is a Lie group. Then this holds if and only if for all classes in the nth spin bordism group of the loop space of BG, in which the domain is our fixed compact spin manifold X, but phi is an arbitrary map from X into LBG, then F1 of Xi acting on this thing X phi is 0 in Z2, where Xi is a natural map from LBG into the n plus 1th BG, essentially taking X phi to X cross S1 with the bounding spin structure, and phi primed is the map to BG corresponding to the map phi there. And then F1 is the classifying morphism for our orientation functor. Okay, and if you think about this for all manifolds X, we see that BP is orientable for all manifolds X and for all principal G bundles P, if and only if this composition F1 of Xi is 0 as a morphism from M against B LBG into Z2. So if we can compute these groups here and the Xi morphism, the F1 morphism, we can know a lot about orientability. If we know that the condition of these things hold for some well-chosen Lie group, such as G is E8, we can then deduce them from any other Lie groups G by this complex type morphism trick. Okay, so then we compute the groups and the morphisms explicitly. We can then answer many orientability problems. Now, if the composition F1 composed with Xi is non-zero, then you know that there are some spin n manifolds X to which the orientations are obstructed, but it may not be easy to decide if some given n manifold X satisfies A, because you're asking whether whether there exists some map into a loop of a loop space or bordism of a classifying space such that representing a given class in the bordism group. So that's why we like to use this KZ4 trick. So because we have an equivalence from the bordism category for EH to the bordism category for KZ4, then when G is EH, we can just replace BE8 with KZ4. Okay, so our calculations show that when n equals 7, F1 of psi is 0. So that tells you that BP is orientable for all principal E8 bundles P over X and for all spin 7 manifolds X. But when n is 8, the composition F1 of psi is non-zero. So this is kind of contradicting the theorem from Cao-Gross-Joyce I told you about last time, which is false. So elements of this thing can be written as X alpha, where X is a compact spin n manifold, and alpha is a 4 cohomology class on X cross Z1, X cross S1. So therefore, you can use Kunith in this case because whatever the homology of X is, because the cohomology of X is free, of S1 is free, we can write alpha as beta tensor the prime cardinal of S1 plus gamma tensor 1, where beta is a 3 cohomology class and gamma is a 4 cohomology class on X. Then it turns out that F1 composes psi of your pair X alpha is the integral over X of beta bar cup the steamrolled square of beta bar, where beta bar is, sorry, that should be a 3 there. Beta bar is the mod 2 reduction of beta in the third cohomology group of X over Z2. Okay, so by our theorem, therefore, if X is a compact spin 8 manifold, then BP is orientable for all principal E8 bundles P over X, if and only if this condition holds. That whenever alpha is a 3 cohomology class, alpha bar has its mod 2 reduction, then the integral over X of alpha bar cup square 2 alpha bar is 0 in Z2. Okay, so combining this with our material on complex type morphisms and so on, we see that if a compact spin 8 manifold satisfies condition star, and G is a compact Lie group on this list, then BP is orientable for every principal G bundle P. So that's a sufficient condition for orientability. When G is E8, it's both necessary and sufficient. Okay, so the case G is UM is what you need for DT4 theory. As an example, the compact 8 manifold X is SU3, does not satisfy condition star, and you can show BP is not orientable when P into X is a trivial G bundle for G any of this list of groups. In fact, you can start with SU3, and there's a sort of obvious principal SU3 bundle on SU3 cross S1. That's the thing which breaks orientability for BP, and then because SU3 is non-orientable, you can use complex type morphisms to deduce all of the other guys here, give you non-orientable problems. Okay, so this contradicts the theorem which was wrong in Cao-Gross-Joyce. Okay, so for Lie groups G not on this list, different conditions apply for orientability or non-orientability. We haven't done detailed calculations, but we have some examples of non-orientability for when X is a 7 manifold or an 8 manifold, if G is F4 or on these things. And for those examples, G would be orientable if G is on this list. And actually, this list and that list together basically make up all of the compact connected, simply connected, semi-simple Lie groups. So it's kind of one or the other. Okay. Now let's consider the question, if X is fixed, let's suppose we prove orientability of moduli spaces BP for all principal G bundles P over X, for example, under this condition star on an 8-manifold. Then we can ask, how can we construct canonical orientations on BP for all P over X, possibly after choosing some data on X? I should say that it is necessary to choose some data. And there are examples of orientable problems on 7-manifolds, for example, such that there is you can find a self-diffeomorphism of the 7-manifold, which preserves the principal G bundle, but changes the orientation on BP. So therefore, a choice of orientation on BP cannot depend just upon the manifold and the principal G bundle. There has to be some extra structure which is moved by this self-diffeomorphism of X in order to construct a canonical orientation. So now we're going to restrict to dimensions 7 or 8, basically where we were aiming was applications to G2 manifolds, spin 7 manifolds, and Calabi-Yau 4-folds, which live in dimensions 7 and 8. Though, in principle, other techniques might work in other dimensions. Then for any group G in our favorite list, we have this commutative diagram of Picard groupoids, where Fg is the orientation functor for G, and Fkz4 is the cohomological orientation functor. So Fg is now the orientation functor controlling what we call normalized orientations on moduli spaces BP. And Fkz4, it's some explicitly defined symmetric monodal functor here. We can define it by defining the maps F0 and F1 on the classifying maps of these things. Okay, so Fg determines orientations on moduli spaces of G2 instantons when n is 7, and on moduli spaces of spin 7 instantons and coherent sheaves on Calabi-Yau 4-folds when n equals 8. Okay, so let's take X be a compact spin n-manifold for n of 7 or 8. We're going to define a flag structure on X, the choice of natural isomorphism zeta in this diagram. So it's similar to the diagram we drew before for BG, but now with the KZ4s. Okay, so some time ago, I defined something I called flag structures on 7 manifolds in 2016, and I showed that a flag structure on G2 manifold determines orientations on moduli spaces associative 3-folds. And with Markus Upmeier, we also showed that flag structures on G2 manifolds determines orientations on moduli spaces of G2 instantons for SUM or UM instantons. This is some time ago. It turns out that the definition of flag structure in this paper is equivalent to this definition here, although that's not a very obvious thing. So this definition generalizes this notion of flag structures in my papers to n equals 8. In 7 dimensions, flag structures on X always exist. In 8 dimensions, flag structures exist if and only if X satisfies this condition star. Okay, so when flag structures exist, then the set of flag structures on your 8-manifold X is a torsor for this mapping space. But here I really mean arbitrary maps, not group homomorphisms. So this is, in general, a huge space. So there's lots and lots of flag structures. So a flag structure is a Z2 choice for each element of this set of isomorphism classes of objects in this bordism category, which is naturally H4 of XZ. So as a way of cutting down the choices of flag structures, we say that flag structure factors via Z2 if zeta, which is the entirety of this outer square, can be factored as a bunch of standard things together with a natural isomorphism zeta primed in the analogous diagram for K of Z2, 4. This is always possible if n is 7. When n is 8, it's possible if a slightly strengthened version of condition star holds, which is that should not hold for any alpha bar in H3 of x Z2, rather than just for alpha bar, which are the restrictions of integral classes. So if that holds, then the set of flag structures factoring via Z2 is now a torsor for the mapping space from the image of the integral cohomology in the Z2 cohomology, mapping space in that in Z2. That's a finite Z2 vector space, so this is a finite choice. And if G lies on our favorite list of Lie groups, a choice of flag structure determines orientations on BP for all principal G bundles. So if we decompose the flag structure as a piece of data zeta alpha for each integral class alpha, where each zeta alpha lies in a Z2 torsor, then for principal bundles, it turns out that the orientation on BP is determined by zeta alpha when alpha is C2 of P minus C1 of P squared. Okay, so that's a consequence of how we define the orientation functor, or the reduction functor from the bordism category to the KZ4 bordism category. So this tells us how flag structures, using flag structures, cuts down choices orientations. So the orientation on BP only depends upon the flag structure data attached to C2 of P minus C1 of P squared, not on the other Chern classes Ci of P. So defining orientations via flag structures is more efficient than just choosing a moduli space for each different principal bundle P. If zeta factorizes via Z2, then the orientation on BP only depends upon this thing in the Z2 cohomology group. There's also a natural choice for zeta 0. So therefore, there is a canonical orientation for BP independent of choice of flag structure if C2 of P minus C1 of P squared is 0 in either the fourth integral cohomology, or if we're factoring via Z2, the fourth C2 cohomology. Okay, so if we're studying DT4 invariants of Calabi-Yau fourfolds, we quite like to know how orientations behave under direct sum maps, where P plus P prime means the associated U of M plus M prime bundle if P and P primed are UM and UM prime bundles. Unfortunately, flag structure is not really very good for studying that question, because this expression C2 minus C1 squared is not additive under direct sums. Okay, so that's a bit of a pain. Okay, so finally, I want to talk about a couple of problems which go beyond orientations of moduli spaces. And the first of this is gradings of Floer theories. Okay, so a well-known example is that if X is a compact oriented 3 manifold, and G is a Lie group, which is usually taken to be either SU2 or SO3, you can study moduli spaces of flat connections on the principal G bundle P. And these are, roughly speaking, critical loci of some kind of a Morse functional on BP. Or you might need to take a covering space here. So by a kind of infinite dimensional Morse theory, under good conditions, you can define instant-on Floer homology groups, HK, FK of P, from a chain complex whose generators are kind of essentially flat connections in some kind of perturbation of this, and then the derivatives in the complex come from flow lines of this this critical dysfunctional. So we can ask, how are the Floer groups graded? So what does the index K live in? So it turns out that if the moduli space BP is orientable, then you can grade HF star of P over Z2. So you kind of, if you perturb this, so it becomes a union of isolated points, the orientation gives you a set of signs +1 or -1 on the points, and then the plus or the minus determines the Z2 grading of those generators. But sometimes we can do better. So the usual orientation Z2 bundle OP over BP is actually the Z2 reduction of a principal Z bundle over BP. This is something which happens because the elliptic operator used to define OP is self-adjoint, and the Z bundle is to do with counting eigenvalues of a self-adjoint operator which cross 0 as you deform the operator. The principal Z bundle has a reduction to a principal ZK bundle, and if this principal ZK bundle is trivializable, then you can grade Floer homology over ZK. It's known, for example, that when G is SU2, instanton Floer homology in 3 dimensions can be graded over Z8. Okay, so you can imagine trying to define instanton Floer homology theory for G2 manifolds in 7 dimensions, using G2 instantons instead of flat connections, and then using spin 7 instantons on X cross R as the flow lines in your infinite dimensional Morse theory. So this would raise a whole lot of horrible analytic problems, which we don't discuss. I mean, this kind of thing is the sort of thing that the Donaldson, Siegel, Donaldson, Thomas research programs are really about. Anyway, we can at least use our bordism category theory to answer questions on the grading of such a Floer theory if you're able to define it. Okay, so if X is a compact spin 7 manifold, for instance, the G2 manifold, G is a Lie group, and P is a principal G bundle, then because the Dirac operator Dx in 7 dimensions is self-dual, the orientation Z2 bundle is actually the Z2 reduction of a principal Z bundle over BP, and we can take it ZK reduction. So then trivializations of these Z or ZK bundles, they're controlled by orientation functors from the bordism category BG into the Picard groupoid of Z torses or ZK torses. And then we can use our bordism category theory to study orientability and canonical orientations. So in 3 dimensions, it's known that you can soup up the kind of Z2 grading to a Z8 grading. We prove a negative result in 7 dimensions. It turns out we prove that if G is SUM or SPM or E8, if K is greater than 2, then there is a compact spin 7 manifold X and a principal G bundle P over X such that these bundles are not trivializable. So it's not in general true that the Floer grading in 7 dimensions for these groups, you can't lift it to grade for ZK for any K greater than 2.
Dominic, in this 3D case, sort of a classical story. So instead of studying a flat connection in the compact and the unitary, you can try to complexify them and consider this as a kind of real cycle. Will it kind of simplify the story with well, I mean, you don't have then to use a sort of infinite dimensional version of the Morse theory. After complexification, you can think in terms of the Picard-Lefschetz, although the critical look, So I don't know, I mean, does it kind of allow people, I mean, to avoid this difficult question about orientation of the moduli space. Yeah.
I'm not sure it is so difficult. And if you frame it using bordism categories, then the three-dimensional bordism, well, basically things, the higher the dimension is, the worse
Yeah,
things.
for these particular groups, yeah, that's
So
fine, but there are some other.
Yeah. Well, well, perhaps I could move on to the next slide.
Okay.
So I'll kind of circle back to your question.
Okay.
If you take a compact spin 6 manifold, then the Dirac operator dx is C-linear, and by looking at twisted Dirac operators, you can define complex line bundle by taking the complex determinants instead of real determinants. So formally, we defined a real line bundle, and then we asked about orientations of that real line bundle. In this case, we can define a complex line bundle living on our moduli spaces BP. And orientation data on BP is the choice of the square root line bundle for this natural line bundle on BP, if it exists. So really, it ought to be called a spin structure because BP is really acting like an infinite dimensional complex manifold. LP is essentially the canonical bundle of this infinite dimensional manifold. And a spin structure on a complex manifold Y is equivalent to choice of square root line bundle for its canonical bundle. So the choice of the name orientation data is due to Yan.
Yeah, I agree that the choice. Yeah, I agree. It may be not terrible because, for example, Drinfeld Stukas, maybe it's more terrible name because I mean there are these Drinfeld Stukas and Stuka means nothing. It's just a piece of something in Russian. It's just an occasion. And here, yeah, but I maybe I have a question, terminological question. I mean, categorically, actually, we have this determinant of the X group, and indeed, we take a square root of it. Of course, it's better to be called spin structure, and that's. But in your four-dimensional case, you're also looking for a square root of some. I mean, again, categorically, if I think in terms of four-dimensional Calabi-Yau category.
Well, the three-dimensional thing is a square root of an object. The four-dimensional thing is a square root of a morphism. That's one categorical level down. It's an easier thing.
Yeah, but kind of. So maybe for me it's kind of I mean, not in terms of names, but it's kind of a similar thing. You want to take a square root. Okay, anyway.
Anyway, I wanted to put up the slide because what you were asking about, I think you were essentially asking about moduli spaces of flat complex connections on a three manifold. That's a -1 shifted symplectic thing. And I suspect what you were asking about was in effect orientation data on those moduli spaces of flat complex connections on a three manifold.
Yeah, probably, yeah. Because I'm thinking in terms of the sheaf of vanishing cycles, and then and also where I'm thinking again, the analogy is maybe not with the Floer theory, but rather with Chern-Simons, which is kind of it's gauge theory on the 3D. You can try to, I don't know, I mean, you can try to factorize, I don't know, the moduli space, the neighborhood of the critical locus of your functional, or rather closed one form. You can try to factorize it in the product of something finite dimensional and transversal infinite dimensional, which is basically quadratic, sort of Morse both direction. And this orientation of the moduli space problem, it in this language, it is translated to what?
I don't know.
Because, if you have, again, I'm thinking in terms of this vanishing cycle, probably if you have a quadratic form, so you can kind of consider it separately, like.
It may just be the orientations of BP for the compact real Lie group, of which your complex Lie group is a complexification. But I'm a bit lost. Anyway, can I put up the last slide and then stop?
Okay.
So this orientation data picture fits into the bordism category framework, at least to some degree. So basically, orientation data for your six-manifold X is rather closely connected to orientations for bundles on X cross S1. So I'm hoping in future to include orientation data in the bordism categories framework, but we haven't worked out the details of that yet. Okay, so let me stop there, and sorry for going over time.
No, thank you very much. It's very interesting. Absolutely. Now, I have a sort of, I understand that you like differential geometry maybe more than I do, but essentially your theorem is formulated like you have a list of some compact groups, and for each group from the list, your BP is nice. I mean, it has orientation, but kind of from the point of view, like people doing Lie group theory, like representation theory, they want, of course, they can go over the series of the particular choices of, say, classical, maybe exceptional Lie groups and check some property case by case, but it's kind of considered as a better approach if you can treat them all simultaneously. And so I understand that your methods are kind of, you wrote 200 pages, it's a huge paper with Upmeier, but what's the problem for avoiding to go case by case?
Well, kind of, most of the interesting Lie groups you can reduce to E8. So if you like, what I've told you today is a reduction to one case, which is the case of E8. And so broadly, we have the groups which descend to E8, and then all the other groups descend from SP2. So if you have orientability for E8, you get orientability for one set of Lie groups. If you have non-orientability for SP2, you have non-orientability for all the other Lie groups. And at least in dimension 8. More generally.
Yeah, I understand. It's rather a question of, of an ignorant person to an expert, because, every finite group is a subgroup of the permutation group, but the theory of finite groups certainly is not always, and actually almost never, deduced from representation of symmetric. So this way to embed an object to some bigger and then deduced property by restriction, it almost immediately requires you to go over some special cases, like different series of groups which you did. So I'm just asking why there is no universal approach. It's a question of orientable. For example, like you have Dirac. I mean, the pieces are quite general, but for some reason the orientation question requires.
We have a general theory, but then the answer in principle depends on which Lie group you input. And yeah, and because there's so many Lie groups, we developed some techniques for comparing them, but you still can't reduce it to one.
Yeah. I mean, it's a sort of it's almost philosophical question. I'm just wondering why one has to check a series of groups instead of finding a general argument why the orientability should exist.
Well, it depends a lot upon the rather detailed behavior of the characteristic classes of your Lie group. Basically.
Yeah. I understand that in your approach, it's
in the level of torsion.
Yeah. Okay. All right. Okay. Now, more questions.
I have a quick question, probably technical, in slide 6.
Yep.
That's the next slide. For the Lie algebra, you said that's the real. Slide 6. You have a Lie group and mapping to from G to H, and the corresponding Lie algebra, the quotient you said that's a real representation. Is that? Oh yes, here.
Okay. Yep.
So because assume that all the groups here are real groups, so the G and H are real Lie algebras. Are you saying that the quotient space carries a complex structure?
Broadly, yes. That's more or less the same as saying big H divided by big G is a complex manifold.
Oh, I see. So is that part of the assumption, or is that always the?
Well, and that's the definition of complex type.
Oh, I see. Okay, so you assume that the quotient has a complex structure. Okay.
Yeah, and as an example, if you look at the inclusion of U1 into SU2, say,
I understand.
Diagonalization e to the I theta, e to minus I theta, then the M is SU2 divided by U2, and that the U1 acts.
That's right. If I have a reductive group,
and SU2 divided by U1 is CP1, which is a complex manifold.
I see. So that's a special type. Thank you.
Yeah, Dominic, and if I would like to deal not necessarily with stacks of coherent sheaves, but more general stacks of Calabi-Yau 4 categories, then, well, according to what you suggest, I should first forget about the categorical structure, take the -2 shifted stack, then look for solve the problem with orientability, yeah? And then
what I would say is that, and there's various, if you want to do Calabi-Yau 4 things, you can look at moduli space of the principal G bundles if G is a reductive complex group. And then the orientation problem for that will come from what I've been talking about for G, the corresponding compact real Lie group. That's one thing you can do. Another thing you can look at is, okay, so there's a problem with looking at moduli space, the principal G bundles, which is you can't compactify them easily because they don't have a kind of nice torsion-free sheaf type compactification the same way vector bundles do. Or if they do, it's not compatible with the shifted symplectic structure. So another nice thing you can do is you can look at perfect complexes with self-dual structures, either kind of orthogonal or symplectic. So you can look at moduli problems of that. And my student Chen Jing Bu has been writing about unity invariance counting orthogonal and symplectic complexes. And if you wanted to understand the orientation problems for those on your Calabi-Yau 4 situation, instead of working for U of M groups, you'd want to know about the orientation problems for either O of M or SP of M for M large. So there are those two different things in which you could, in principle, use these techniques to try and prove orientability for algebraic geometry Calabi-Yau fourfold moduli problems.
Yeah, and beyond geometric moduli stacks, if I have, I don't know, like
if you just produced a shifted symplectic stack by magic, I don't think our techniques can tell you anything really about its orientability. I mean, this happens because you can think about homomorphic vector bundles as complex vector bundles with connections, more or less, and then start studying classifying spaces of things. But
yeah, okay, yeah, I understand. Yeah, okay. More questions? Well, if there are no more questions, so thanks for two nice lectures, Dominic. Very interesting, and your huge paper is in the archive, so people interested in the details can look at it. Okay, thank you. And
thank you.
This is it for today.